This is Ertan Taskin from Ozon Engineering, and in this video I'll be talking about the TwinMesh software with features and applications as well as a tutorial. TwinMesh is an automatic high-quality grid generation tool for rotary positive displacement machines. That means the simulation is not performed in TwinMesh, rather the grid structure is established. The simulation workflow is shown here as from left to the right, such as the grid for the machine is generated with TwinMesh. And then the stator grid is actually brought into the model with an additional tool such as ANSYS meshing. The pre-processing and the simulation can be done either CFX or Fluent. And then the results can be post-processed with either CFD post or Nsight. The grid can be generated for many types of machines in TwinMesh, such as external gear pumps, internal gear pumps, screw compressors, lobe blowers, eccentric screw pumps, and so on. There are many benefits of using TwinMesh, such as it provides efficient workflow, maximum flexibility, as well as mesh control and quality. One of the important features is the interface is fully automatically generated between the meshes for 2D or 3D structures. After the mesh generation, ready-to-run input files can be exported very easily to the ANSYS CFD. The other important feature of the TwinMesh is easy geometry scaling. It can handle the grid generation for very small gap size, which is a typical feature for these kinds of pumps. Furthermore, user can fully control the mesh size and mesh resolution, as well as boundary layers and local refinements. Many additional details and features of the TwinMesh can be found in this reference recording. Let's go through sample 2D application of Lobe Pump. When we open the TwinMesh, the pop-up screen is actually asking for which type of machine we will generate mesh. And as you see, the Lobe Pump, internal gear pump, and screw compressors, etc. From scrolling left to right, we could choose what type of machine we will work on. So in this project, we will do the Lobe Pump. Let's read the geometry file. Import geometry. And for this example, we will do Lobe Pump 2D rotor. And this brings us the two rotor structures. Now, first, with the control key and the left mouse button, we can select a portion of the rotor. And then with the right click, we can select all the connected curves. And we can group these so that when we select again with the control, we can select everything in once. Similarly, for the other rotor, let's select them, make the group. Okay. So let's define the boundary definitions. For this one, again, right click, boundary definition, rotor wall curves are 1. This one, rotor wall curves are 2. So different colors represent that they are 2 different rotors. Let's go to geometry, and we will define the mesh per pitch angle of 60 and with a rotor length of 1 millimeter. Since this is a 2D geometry, there's basically no length in the Z direction. So let's come to rotor 1 and define the number of lobes. This is 3. We're not changing the position, but the case radius. So we're going to define the case 120 millimeter. When I type in this number, you will see that on the screen, the circular casing appears. You have an option of bringing this as an additional IGES file, of course, but since it's typically mostly a circular feature, it's relatively easy to create it on the screen. Similarly, what we can do on the R2 side, define the number of lobes. Casing radius is same, 120. But in this time, we don't see it immediately on the screen, right? Because we have to create a new axis position for this one. So R1, or this lobe, and this R2, the other lobe, they are separated between from each other with a 180 millimeter distance. There you go. Now we have a casing appears for R2. We can quickly take a look how the lobe operation looking. So I'll actually demonstrate up to which angles we will go. So as you see, we reached to the 60 value, which was, remember, the pitch angle that we described. So for 120 degree of a rotation, if you will, we defined 60 motions. It's typically 1-to-1 though. We should have done 120 rotations, but for the sake of this tutorial, let's consider 60. Back to the original state. So I'm going to demonstrate you that now with the casing and the rotor features, they are pretty much right. They are tangential to each other, if you will. And but we can create a small gap, which can be done fairly easily here in scale value, right? So let's create a gap of 0.1 millimeter. So when I hit somewhere on the screen, you see how they are separated from each other. That's pretty much 0.1 millimeter. And we can roughly measure this. As you see, that is so. And why do we need this? Because we need to put enough computational cells to resolve the boundary layer between the stator and the rotor. That's why we need a clearance. So we can put computational cells there. We will do very similarly on the other side. Let me demonstrate here too. Let's come to rotor 2 and a scale value of 0.1, and as you see, they are also separated. Okay. Now, let's create the interfaces. That right-click the geometry and generate the current interface. See, it proceeds and it creates the interface between these two lobes, particular to this position. And we will continue to do the same thing for all the other positions. That's why we're going to come here, generate all interfaces. And after a few minutes, all the interfaces are generated. We can even take a look at how the interface is actually moving with the motion of the rotors. Let's also check all interfaces icon just to perform a similar operation. So we will move on to the mesh generation. Let's click mesh generation, and we're going to put the maximum element size as 4.2 millimeter. First element height, inner is 1, outer is also 1. Number of elements radially, 15. Number of nodes on the interface, 43. You can definitely play with these numbers and see how are they impacting the overall mesh quality. Number of elements in Z direction. Let's keep it as simple, so let's make this 1. Right click on mesh generation and choose generate on current mesh. Current meaning on the corresponding position of the rotors. As you see, it was very quick. The mesh is generated for this particular position. If I zoom in, you will see how the mesh squeezes in the smaller regions, particularly on the interface, as well as on the smaller gaps that we generated. There are plenty of cells there. All right, now let's check the mesh quality. In order to check the mesh quality, we can select this button, and there are a few parameters that we can consider. This minimum angle is automatically presented here, and minimum angle greater than 18 degree is recommended, and for this particular mesh, it is already satisfied. Since this first mesh seems to be fine, let's generate all the other meshes very similarly. Generate all meshes. As you see, one by one, the mesh is generated for different positions. So for all the positions, the mesh is generated. And we can quickly take a look at the minimum angle does not go below 18. Let's perform the simulation case setup and export. For that, we're going to come to here, and we're going to define or select the CFD solver. In this example, let's keep ANSYS CFX. And this is not a 3D problem. Let's make it 2D. And for the fluid model, let's consider incompressible with cavitation. So far, we have created the mesh or the grid structure of the rotating machine with TwinMesh, right? But we have the stator that should be attached to the geometry. So that could have been done previously with a different meshing software, and we can actually come here and select the corresponding file and add to the problem. Over here, right click, import stator mesh, and that is the corresponding stator. And the unit is meters, except let's save the project. And I am gonna keep the new project name as it is. Okay, let's define the other features such as the rotational speed, revolution speed of R1. So let's make this 400. Inlet pressure is 1 bar. We're not going to play with the temperature here. Outlet pressure is 3 bars. And number of time step per run, let's make this to 720, which is going to correspond to 4 full revolutions with the described rotational speed. Maximum coefficient loops, let's increase this for the sake of the quality of the calculations. And start method. Instead of serial, we're going to select Intel MPI local, and depending on the availability, we can increase the number of processes. Let's keep it as 2 for this case. In order to export the generated mesh, let's come to File, Export all files. So before clicking OK here, let's select Open the Solver Setup after the export. So it's going to open the CFX-Pre to us automatically. And there you go, CFX-Pre window popped up. And as you see on the screen, the corresponding geometry is brought up with all the details and the boundary conditions and locations as they are all described. Let's save the setup CFX file. New project. Okay. And then let's open the solver. Yes. And we will start the run. It's going to take some time to reach the conversions. After the simulation completed, we can bring the solution to CFD post or Nsite to perform detailed post-processing activities. In this case, I brought the solution into CFD post, and we can definitely do multiple things, such as take a look at how the lobes are, the machine is operating on a cross-sectional plane. Similarly, we can bring the vectors and perform similar post-processing activities. When the machine operates, how the flow field changes. You can definitely take a look at the pressure distribution, etc. And with that, this demonstration video is concluded. Thank you for watching.